everyone. Thank you very much for joining to the fifth session of Bootcamp's GeoHackathon 2023. My name is Jawad Shokri. I'm working as a postdoctoral researcher at University of Manchester, and I've been involved in organizing GeoHackathon for the past 3 years. Today, we have the opportunity to, just sharing my screen. I hope you can see it nicely. So we are halfway through the bootcamp sessions, and today we will have the honor to have Luca Fava from OMV Petrom. A very short description from Luca. Luca holds his master's degree in geology, and he earned his PhD in sedimentology from the University of Parma. He has more than 20 years of experience in oil industry, and he has as a geophysicist, and he has worked in different countries and have worked on different projects. He mainly have been involved in seismic interpretation, seismic inversion, attribute analysis, and deep depth conversion, among others. And also the techniques that he used was applied to hydrocarbon exploration to improve the success rate of hydrocarbon exploration technically, and recently has become interested in application of machine learning techniques to exploration. As you can see on the last section of his presentation, he will talk about that. So without further ado, Luca Fava, thank you very much for being here today, and the floor is yours.
Thank you very much. Yeah, I would like to apologize for the fact that my camera seems not to work today, so you won't see my face, but I hope you can see my screen and hear my voice very well. At the end of the day, you're not missing that much. So, yeah, thanks for the introduction, and thanks for the opportunity to give you this lecture. I would like to give you another kind of visual introduction to my career. As you heard already, I started actually my career when I was very young, doing some IT programming using BASIC and Pascal. So I'm still kind of interested in this kind of stuff. But then I moved to geology, doing sedimentology, and as you can see from the pictures, a lot of field work. So a lot of geology that enters in the geophysical interpretation of seismic. As we will see later, it's very important to have this geological understanding in order to interpret seismic data. So this is a very schematic agenda of what we are going to talk about. I will start doing some very basic general concept about seismic interpretation, meaning what we are looking at when we look at seismic data, what's the meaning of these reflections. And then we will talk how we do well to seismic ties. So basically how we connect the seismic data that is acquired in time with the depth data coming from wells. And we talk about also that conversion. So the first point, as I said, is this one. So what is seismic reflection mainly? So the acquisition of an image of the subsurface that needs to be interpreted in order to understand what's going on below our feet, basically. So very simply, you can see this very simple model with the different layers of different rocks, and each rock has different characteristics. What is important for the propagation of sounds through these rocks is the velocity and the density of this different layers. When we have a an interface with between two different rocks, so between two layers with different velocity and density, we do have what we call a refraction. And this is basically the very basic model about seismic. So as I said, we have a layer 1, a layer 2 with two different velocity and density, and an interface. And when we have a wave that is coming down from surface, from our source, this wave is partly reflected based on some specific law that I'm not going to talk about. And some of the energy is actually transmitted downward. So at the reflection interface, we have a reflection coefficient that is calculated using velocity and density of the two different layers. And as you can see from this, let me use the pointer, just a second. There you go. As you can see from this scheme here, let's say that we have two different layers with different velocity and density, and that means also different acoustic impedance. So we are moving from a lower acoustic impedance to a higher acoustic impedance, and that is creating a reflection coefficient. This reflection coefficient is convolved with a wavelet that is basically the shape of the energy that is traveling through the rocks. And the result is a trace, a seismic trace with peaks and troughs. When you stack together different traces, of course, you have a seismic image. Yeah, that's what you can see here, for example. So when we move from the weathered zone, the first layer onshore, to shales, we have a positive increase of acoustic impedance, and then we have what we call a peak in this case. I'm not going to talk about polarity, not to confuse you guys, but the important point is that basically when we look at seismic lines, what we see are the interfaces between different rocks. So that's basically what we need to understand. Good. This is probably the right place already to talk about a general problem that we have with geoscience, basically, especially in the oil and gas exploration, but also for geothermal needs, because we need to understand what is going on the subsurface also in that case. This problem is the scale problem. As you can see from here, from right to left, we can see the different scales at which we can analyze rocks. Okay, so if we have a thin section, for example, a very small slice of a rock, and we analyze that on a laboratory, of course, the scale is very small. We can go down to 1/10 of a millimeter. When we look at an outcrop, a rock in a beautiful environment like this one in the picture, you see for scale the cars here down, and this is a beautiful hill with outcropping rocks, and you see this small point here is basically this small area where we can look at rocks directly. So we can go down up a bit on the scale, but still is very small. We can see fossils, we can see stratigraphic feature, we can see sedimentary feature, and so on. When we drill a well and we acquire a log, that's basically the scale we are looking at, right? So still very detailed. When we look at seismic data, the scale is much bigger. You see here, those are a peak, a trough, another peak, and another trough, and that's the scale, right? So when we are lucky and when the seismic image is very good and the frequency content is high, we can discriminate objects down to 15 meters. Sometimes we are not that lucky, and the scale is a bit, the resolution is a bit higher. Or actually, the resolution is lower. Okay, so that's the concept of vertical and horizontal resolution. So there's a limit. I'm not going into details because I'm assuming that I'm talking also with the data scientists that don't know that much about geology and geophysics. So I'm just giving you a flavor of the main concept. The point here is that the seismic data have a limit of resolution, both vertical and horizontal. Okay, so below this limit that is defined by the frequency that we have acquired with the data, we can't resolve objects smaller than that. Okay, that's a problem that we need to keep in mind. Now, as I said, seismic is acquired in time. That means that when we acquire the data tell us how long the energy took to travel through the rocks and bounce back to surface and to be recorded. So the time that we are talking about is the time of travel through the rocks, okay? But then all the wells are measured in depth, of course, because we're drilling through the rocks and we know exactly at what depth we encounter that specific rock. So we need to have a way to connect the information from wells to the information from seismic. We have different scales, as we have seen. We have different velocities that we use, so we need a way to do this tie, and the tie is done through the well to seismic tie. So that's basically, we need to estimate a wavelet, we need to generate a synthetic seismic, this one in blue, using the logs, using the sonic log that is measuring the velocity, and using the density log that is measuring the density of the rocks. And we can calculate then a computed impedance here, and we generate a synthetic trace, and then we put the synthetic trace next to the real seismic trace, and we can match the two images. How good is the match is calculated with the correlation coefficient that you can see here. In this case, the value is 79, so that's really good, of course. One will be perfect, of course, but we can have different values. It depends very much on the quality of the seismic data, or on the noise, and so on. But this is the way in which we can say this interface between different rocks. You see here the velocity is jumping up and the density change as well, is represented in the seismic by this trough. This peak is representing another interface between different rocks, and so on. Okay? Good. So the general outcome of an interpretation is to build an image of the subsurface. So we need to build a map, as you can see on the right, a map of one of those interfaces, possibly also more than one map. Here you can see a beautiful example of a structural framework. So it's basically the 3D definition of a package of rocks with different layers and different velocity and density, of course, as we said. And for each of these boundary between the different colors, we can build a map. So we have a 3D image of the subsurface that can be used to explore for oil and gas in my case, but also to explore for geothermal, as we will see later on. So we know exactly where these interfaces are, how the folds are cutting through the rocks, and so on. Now, As I said, most of the seismic lines are acquired in time, so they need to be converted in depth, meaning we need to build a velocity model like this one on the left that can push down the horizon that we have interpreted and the fault that we have interpreted on the seismic down to the right position in depth. The velocity model is very important, as you can see from this synthetic example on the right. This is a synthetic depth model. You see how it's been built. So these layers are horizontal, but then you see the image in time. So the seismic image has this pull up here, and that's because the velocity that were used to build this synthetic synthetic seismic traces were not correct. Okay, so you have a pull up because you have a too fast velocity above, and this horizon has been pulled up. Okay, so it's very important to have a correct velocity model to do depth conversion to avoid artifacts like pull-ups and push-down. And that's basically an explanation, let's say, of this effect. If you have 3 layers with sand and shell on top, limestone that normally is a very fast rock in the middle, and another unit below, the 5,000 meter per second velocity of the limestone is pulling up this interface here, and that's an artifact, and that's something that we need to deal with. Now, depth conversion is very different from depth migration. So there are 2 very different concepts. Depth conversion is just a vertical process, is a vertical stretching of the seismic data in time to depth. So we have a 2-way time map that has been built, peaking horizons on seismic, and we stretch down using a velocity model the map to depth. Depth migration is very different. Depth migration means that we need to build a velocity model to have a better image of the seismic. Okay, so when we have acquired the raw data, the raw seismic data, we need the correct velocity to image the subsurface in the correct way. One classical example of a possible problem when you use the wrong velocities or non-migrated data is this bow tie shape that you can see here before migration. And after migration, you manage to see the sink line. So this very geological feature, very important geological feature. Okay, so this is just to remember you that depth conversion one thing, depth migration is a different thing. Depth migration is about processing. Depth conversion is about after the interpretation, how we put down to the correct position our maps. So for the depth conversion, we need, as I said, we need to build a velocity model, and that can be done in different ways. It depends, of course, on the amount of data that we have. It can be just a simple well function built using basically an average of the sonic log, for example, like in the example on the left. We can use a layer cake method. That means we can build maps of velocity, of interval velocity between 2 horizons, or we can have a velocity cube, a very sophisticated way to see also lateral variation and vertical variation of velocity. Of course, it depends on the scope of the work and also on the amount of data that we have at our disposal. Right, so having talked about the general concept, we can go down now to the real interpretation. So what is interpretation and how we do it? As I said, it's very important to have a geological concept in mind to do seismic interpretation. For example, if you look at this seismic line, and if you're not familiar with geology and with seismic interpretation, it could be very difficult to find out what this image means, basically, right? What we need to interpret in this. It looks like, I don't know, I'm probably very old, so I still remember when television was black and white, and sometimes it was really disturbed and the image was really fuzzy. It looks something like that, right? But then if you put some geological knowledge and geological concept, you can interpret this seismic line. And that's not that easy, of course. It needs some training and some geological reasoning. Now, so what that means to have a geological understanding, it means that you need to know some basic sedimentary basins, and to know which kind of faults you're going to expect in this kind of tectonic setting, and so on. This is just an example of the different tectonic setting that you can encounter when you do seismic interpretation. Of course, everybody knows plate tectonics. We know that we have the continental drift, so we have the seafloor spreading with some oceanic crust forming, and so on. And then on a sort of a cycle, we can have then the closure of an ocean and the subduction and the collision between different plates. All these different moments during this sort of cycle give origin a different structural feature and different faults. So once you know in which geological setting you are, then you know which kind of faults you would expect. For example, if you are in a continental collision, you know how it works, you know which kind of basin do you have, you know which kind of faults, truss faults like these ones. You know that you can have what they call piggyback basins and a four-deep, so a filling of these different basins, and you have an idea of which kind of geometry you want to see and you would see in a seismic line. That's an example from a seismic line of exactly the same geological setting. So you see the truss on the left here, you see the basically the top of the basement, if you want to call it like this, and you see the overlap of all the sedimentary strata. They are filling up the four deep in this case. If you are in a passive margin, like could be, I don't know, the West African margin or the margin of South America, like in Brazil, you would expect different kind of faults, not thrust, but normal faults. In this case, you will have the presence of a very thick and mobile salt layer, this one in pink, and so on. And then you will have some sedimentary deposits like turbidites within the younger part of the sequence. Again, you need to have in mind a geological model before you look at seismic. That's an example of something very similar. That's from Brazil, actually. So you see the normal faults at the bottom, then you have the salt, in this case in blue, and then you have very distinctive and particular faults on top of the salt, creating different kind of fish, right? So I'm not giving you, of course, a crash test in passive margin geology, but the point is that I want to stress the fact that you need to have a geological understanding of what you're picking before you start picking. That's another example. In this case, we are talking about fracture basement, and that's very important, for example, for geothermal, because in geothermal, what we look for in a geothermal project is to find some temperature, and to extract that temperature, we need to move some fluids through that rocks at the level where they have this temperature, and we can bring this water or these fluids to surface, so to bring the temperature up. In this case, you can see the different scale again. This is a very fractured rock that could be similar to a basement. And in this model, you see all the network of fracture and faults that we can encounter in this kind of environment. And here is a seismic line within this one in red, the basement. Very fractured, of course, because you have a lot of faults and also a lot of fracture. And that's actually a target also for hydrocarbon exploration. But the point is that, again, you need to understand what you are looking at in the seismic and trying to figure out what to pick and how to pick it. Good. That was about the structural setting, and the structural setting is very important. So we need to understand basically the box, the container of our fluids, water or hydrocarbon, that depends on which kind of business we are in. But then we can also interpret stratigraphy within using seismic images. In this case, I'm showing some examples of stratigraphic terminations. During the 70s, actually, the ExxonMobil group was developing this concept of sequence stratigraphy and first of all seismic stratigraphy. So the concept was we can analyze the stratigraphy, so the evolution of a basin, identifying on seismic this termination. So you can have on-laps, you can have down-laps, top-lap, and erosional truncation. And these are simply what they are. So geometrical relationship between reflectors. So, and reflectors, if you remember one of the first slides, are interfaces between different rocks. Okay, so that's the basic concept. And the group working on Exxon at that time, they recognized that they could see a pattern in this stratigraphic termination, and they could recognize different sequences within seismic images, and that can really improve the interpretation of a basin and the understanding of a basin, and of course finally it can improve the exploration. Good. So we can interpret stratigraphy, but we can also interpret specific sedimentary features like channels, like in this case. It's a very detailed image of a channel complex. You see on the upper part the raw seismic, and in the bottom part the interpretation of this seismic. So you can interpret the feature, so the geometry of the channels, but you can also interpret different phases, and we will see what that means in a few slides. This is an example of clinoforms. So when you have a delta that is prograding, so it's moving into the sea, you have this very characteristic deposition and these very characteristic geometries. Again, we are picking geometries in this case, right? All right, now we can move to other particular features that we can encounter. And again, they can be very important also for geothermal projects like volcanics. This is an example of a volcano that can be interpreted quite clearly on seismic lines. But be aware that sometimes it's not that easy to recognize a volcano or to discriminate between a volcano, for example, and some other very particular features like a carbonate buildup, a reef, basically. You need, again, to have an idea what you're looking at and to have some experience about it and some geological knowledge to be able to discriminate the two. Or you can have other feature kind of similar to the previous ones. These are salt diapiers. Again, if you have salt or evaporites in general, they can be kind of mobile and they can move through the different rocks layers and actually create these small pillows, intruding actually in younger rocks. That's a very clear image of the top of the salt here. As you can see, that different velocities are creating a problem on the image. And so you can't really see the base, and you can see this dramatic pull-up of the horizons below the salt. That is very, very fast. Good. So all in all, what we do is try, as I said, try to understand and to build a geometrical model of the subsurface. And then we do the interpretation of horizons, and we try to understand also the stratigraphy and possibly the geomorphological feature that we can see. Sometimes the interpretation of seismic line can be complex, like in this case. But if you try to remember all the concepts that we have been talking about so far, we can see here some unlaps, for example. So you can see an unconformity. You can see a fault. Actually, you can see many faults, but this is a very important one. And then you can see some stratigraphy. So you can see again other overlaps. You can see the different thickness of this package nearby the fault and getting thinner and thinner on the other side. You can see other faults that are crossing each other. So, and then you can start to think about the timing of those faults and the meaning that this faulting can have in terms of migration of fluids or stopping the fluid to migrate. There are many different concepts that you can try to understand using the interpretation. Right. Again, you need to have an idea of what you're picking and what makes sense in terms of geology before you do your seismic interpretation. It's not just picking colors and making nice pictures. Okay, the seismic interpretation can be done at small scale. You can interpret what we call in hydrocarbon exploration a prospect or a lead. You can interpret a small area because you want to evaluate if it's possible to develop a geothermal project, but you can also do regional scale interpretation, like in this case. And yeah, that's all the amount of information that you can extract from a single seismic line, just looking at the fault and looking at the geometry as we have seen before. So the termination of the different reflectors, the top lap, the on laps, the unconformity, and so on. And on top of that, yeah, using that actually you can build a stratigraphic framework. So basically, you can define different units. They represent a specific time and a specific evolution of the basin. And you can also define seismic phases. So what is a phases? Phases is a Latin word that means actually look, how a particular rock or a particular area of seismic, in this case, looks, right? And we can define different phases if you can define different characteristic of this part of the seismic line. In this case, for example, we can discriminate between phases with tabular shaped medium amplitude reflection with good continuity and high frequency, for example, or we can have otherwise a wavy shaped divergent reflection with a high amplitude and poor continuity, and so on. So you can define different patterns in the seismic image, and based on that, you can define these phases. And of course, why we do that? Because these phases have a geological meaning. Okay, if you see something like this, for example, you start to think that maybe there is a channel there. If you see something that is completely blank, well, maybe we are drilling, we are looking at some basement or maybe volcanics or stuff like that, right? So the idea is that you can define different patterns, and once you define these different patterns, you can correlate those to particular rocks and particular events in a geological scale. Right. This is another example. So the seismic interpretation is actually a way to describe the evolution of a particular basin with just colors and geometries and peaking horizons, right? It's really telling a story, but you need to understand what that story means in order to make sense, in order to build a story that makes sense. This is an example of a beautiful geoseismic cross section with the interpretation of normal faults at the bottom, as you can see, and then you see the clinoform here, for example, other faults. You can see unconformities. You can see a lot of stuff. And that's a beautiful example of what is the outcome of the work of a seismic interpreter. Good. The last point that I want to touch upon is the geomorphological feature. What that means? That means that we can define features that are like channels, they are deltas, they are so feature that can tell us about the positional system that was at that time, at that geological time in that particular area. Here you can see on top right here a beautiful river, meandering river, and also another one on the bottom part, a meandering river, in this case in a forest. And we can see something very similar on seismic. You can see here on this beautiful image from a paper of Bosamatier et al. Is this a river? No, not necessarily, because we see these meandering channels also in the sea, basically below seawater. So it's not a river, but it's a channel that is bringing sediments from the margin of the basin down to the basin. Those are other examples of this kind of geomorphological feature. Here you see this beautiful image with two channels cutting into the margin of the basin, the platform, and then you see the position of these slopes at the bottom of the slope. And again, here other examples of meandering channels with abandoned meanders and other stuff. So what this picture tells us is that we can see a lot of information about the positional system that was there at that time, right? So if we go back here at each of these interfaces, at these horizons, we can look at them on a map and extract some attributes from the seismic data and try to understand what was that area how that area was looking, right? Which kind of sediment did we have? Where are the sandstone? Where are the shales, and so on? So it's when you do an extraction of seismic attributes at a particular geological horizon, it's like having a snapshot of that particular area at that particular time. Good. So all in all, my message is that geophysics without the geological understanding can be dangerous. At the end of the day, I'm sure you have already heard about this saying, and this saying has been always very popular among the geophysicists: garbage in is garbage out. Okay, so without the understanding and without the good data, you can't really get out the right answer, basically. An interesting quote is from Harold Reed. So the best geologist is the one that has seen the most rocks. That's why I was showing you picture of outcrops at the beginning. So you need the geological understanding to correctly interpret the seismic data. Now, few words about the interpretation workflow and some words about the pitfalls, the possible pitfalls. So when you do seismic interpretation, again, it depends on which data do you have. You can have just 2D seismic lines, and that means just a slice of the subsurface. And you can have, for example, as you can see in this example here, just few lines, and you have to connect them and do the interpretation only on those sparse data. And then if you want to make a map, you have to interpolate between. Okay. This is an image showing how seismic interpretation was performed back in the days, meaning with pencils on a paper. And you would really draw your interpretation on top of that printed seismic line. Luckily, now we have 3D cubes, so a much more detailed and refined way of looking at the subsurface. And you can do interpretation on a very regular grid, like in this case. Here you see basically on a map view the same horizon that you see here in 3D. And then maybe you can infill between this grid using auto tracking. Now, one of the problem, again, we are coming back to outcrops, to the geological understanding, and to the examples from nature. One of the problem in seismic interpretation is to interpret fault, but also to jump over fault, meaning, let's say that I'm picking this horizon here, I need to know where to jump across this fault, right? And the fault is a fracture on the rocks. can see this beautiful example here. Sometimes it's not that easy, as you can see from this example, right? So how do I pick this one? Where do I go after this fault? Am I picking this horizon? Am I picking this one or this one? Sometimes it's not easy, okay? And this is an example from seismic, same stuff. You see the fault, just pick the most important, not all of them, but you can see that it starts to be complex. Maybe you can do the interpretation like this, but it's not always easy. Sometimes you are really in doubt. How can I pick this one, and then how do I jump? Where do I jump over the fault? One technique that can be used to overcome this problem is to make a composite line and going basically around the fault, because the fault is not continuing indefinitely. It will stop at some point laterally. So maybe you can turn around and see where you connect your interpretation. This is an example. So you see the seismic line here from A to B to C, D, and E. And here you see on a map, A to B to C to D and E. And this is the initial interpretation of a fault. That is this one. Where I'm going on this side, I don't know exactly, but if I do this loop, I can do my interpretation. Extend the interpretation here, and I see the point appearing here. So then I'm sure that I can do the interpretation because I turn around the fault. Okay, that's something that can be used in when you have doubts where to go. Now let's talk about auto tracking. We discussed before briefly. So just to remind, a seismic line can be seen in color, as you have seen with the red and blue or whatever other color scale you prefer. But you can imagine also the seismic composed by different traces with peaks and troughs, right? Now, what is auto tracking? Auto tracking means that the software that you're using to do the interpretation do analyze this waveform or the shape of the traces, and can compare the traces with the traces next to it. And so trying to propagate the interpretation based on the similarity of these traces. Okay, there will be a threshold over which the propagation will stop. But the basic idea is I want to extend the interpretation to traces that are similar to the one that I've picked. And the one that I pick means that you just put a point that is called a seed, and then you let the software to do the automatic interpretation. So for example, this is a seismic line in 2D that is this within this yellow square here, and this is a view in 3D of the cube. If I put a seed here and then I do the automatic interpretation, that's the result. So I have a 3D extension of this interpretation just with one click. Some more advanced softwares can do the automatic picking of the entire cube, and they can create different patches of horizons based on the similarity of the traces. So maybe that's an idea for doing some automatic interpretation using machine learning. Good. So the final result and the final outcome, the final deliverable of a seismic interpretation is the building of a structural framework. So you have a box and the geometry of all the faults and your horizon, and then you can analyze them in details. Good. Now, talking about interpretation pitfalls, I guess by now you got the point. You need to know what you're picking before you pick it. So you need to know what you want to see. Otherwise, you're not going to see it. You see only what we know. Okay, that's a very important concept. You need to have a geological model in your mind before you do the picking. Otherwise, it's really tough. And on top of that, there are biases. And there has been recently some work, some tests made using interpretation skills of students, but also of very expert people doing interpretation. And then basically the outcome of these results are that is very important which kind of background and which kind of experience the seismic interpreter has, because that is very likely to impact on the interpretation. So the biases are quite strong and very difficult to get rid of. That's again something to keep in mind. And maybe I throw there a question. Maybe machine learning is a way to avoid these biases or to average out these biases. I leave it to you, a possible answer, because I don't have a clear answer so far. Right. So we do the interpretation. We do have a geometry of the subsurface, and then we look at the seismic attribute to try to extract as much as possible of information from the seismic data. We want to squeeze the seismic data to get as much as possible out of it. Seismic attributes are basically quantity extracted from or derived from seismic data, and they can be analyzed in order to improve the information, basically. So we need to better understand where are the faults. We use like kind of attributes that can detect edges, for example, like variance or semblance or whatever software you're using. Probably they have a different name, but that's the same kind of algorithm. You can have edge detection methods and so on and so forth. The result will be an image such this one on top right, that is emphasizing basically the discontinuities within the seismic data, and that could be useful in order to pick the faults with more precision. We can have lithological and stratigraphic attributes like sweetness, RMS amplitude, spectral decomposition, and those are attributes that can help in depicting a delta like this one with channels, right? Or they can give us information about porosity, for example, like sweetness. So actually giving us information about the real characteristic of a particular rock. For us in the hydrocarbon exploration, of course, we do have a very important third kind of attributes that are called hydrocarbon indicators. They can indicate hydrocarbons, so gas and oil, of course. And here you see a beautiful example of an amplitude that is showing gas in a famous field that I'm not going to name. Right, that's an example of continuity attributes or variance or whatever it's called. Is basically again an attribute that can detect discontinuities, so faults. That's a very important one because it can allow us to pick in much detail all these faults. And again, that can be important for, as I said, for migration of fluids, also in a geothermal project, but is also very important for safety when you start to drill a well. You want to know if you are close to a fault, if you are crossing a fault, because it can be a safety issue. And these are just some example of direct hydrocarbon indicators. We are talking about amplitude anomaly, flat spots, and bright spot, and so on. I'm not going into detail unless you want to know something more, because probably it's not will not be the focus of this hackathon. So, but that's something that we can do, and we can extract in terms of information from the seismic data. So also information about the fluids within the rocks. Okay, so those were kind of calculated attributes. So basically you have your own your raw data, you do some math on it, and you can calculate these attributes. Then we have derived seismic attributes like seismic inversion. Remember this picture at the beginning? So we start from the acoustic impedance, we convolve the wavelet over it, and we get a seismic line. If we go in the opposite direction from the seismic line, we do the inversion, we can derive the acoustic impedance. Okay, so we are going back to the impedance, and that's related, as we know, to velocity and density of rock layers. Just one word of caution, of course, the seismic inversion is an inverse problem, as all the inverse problem suffer a big problem, that is the non-uniqueness of the solution. So you can have basically many models that can explain your seismics. So you will never be sure that your answer of the seismic inversion is correct. But that's something that has been done and is done on a regular basis on the oil and gas exploration, trying to understand better the subsurface. And that's an example of seismic attribute cube derived from seismic, okay, from a seismic inversion. Another application can be you do the inversion and you calculate different cubes, not just the amplitude, the acoustic impedance, sorry, but also the density and other parameters. And using those, you can even calibrate your seismic cube to porosity volumes. All right, so this is again an attempt of looking at the specific characteristic of rocks in the subsurface, starting from seismic data. And that's another beautiful example of seismic line extracted from a cube with porosity. Then you can compare with the porosity logs from wells, so you can calibrate this information with real data from wells. Good. Now, I'm gonna close down with a few words about seismic interpretation for geothermal projects, and a few words also about machine learning. I'm not an expert. I'm just trying to get involved in it. So I'm not pretending to know more than I do, but I will just give you some flavor of what we can do or what can be done for seismic interpretation using machine learning. So about geothermal, as I said, one of the crucial parameters for geothermal is, of course, temperature. But to extract the temperature basically from subsurface to surface, you need a fluid. Normal is water, but you can also use other fluids. But to have fluids and to flow fluids through the rocks to capture the temperature and to flow it to surface, of course, you need to know the properties of the rock or the reservoir rocks. So you need to know the porosity, you need to know the permeability, maybe the fracture, and so on and so forth. All these parameters can be derived using seismic data. So the seismic methods that can be used for a geothermal project are, of course, you need to understand the structure, of the rocks. So you need to do the structural interpretation to understand the volume of the rocks where the temperature is high. You need to know the faults for both to minimize drilling risk and to understand the migration path. And you can use the seismic inversion to assess the porosity of the rock, for example. Right. The main issues, of course, are similar to what we face onshore for hydrocarbon exploration. Onshore, the acquisition of the data onshore are affected by statics. The velocity model are very complicated, and polarity can be a big issue on seismic. Good. So what about machine learning? As I said, I used to do to use BASIC and Pascal to do some coding when I was young. Recently, of course, with all this talking about machine learning, I went back to it and tried to do some stuff, and I'm looking into it in more details. And what I find out is that as a geophysicist, we have been doing actually some of the machine learning technique for ages, like clustering. That's something really normal for us because we want to define rocks with particular characteristic, like rocks filled with gas, like in this graph. So if we are able to cluster this point, maybe we can see them on seismic. And the same goes for the ABO analysis that we do and so on. So I think that there are two main trends in the use of machine learning applied to geoscience. One is clustering, as I said, so is the unsupervised analysis of geophysical data. This example is from a paper from Roden et al. Basically, they did a classification of seismic data using self-organizing maps, and that's something that can be done, as I said, to define, generally speaking, phases with the seismic data. What those phases means, that's another story, but that's the approach. You basically use different seismic attributes as your features, and you do the clustering using a self-organizing map. The other approach is about real interpretation, meaning picking a horizon of faults. In this case, the approach is always a supervised approach, meaning that you need to train the algorithm. So you need to show the algorithm what is a fault, what is an horizon, and train the algorithm using those labeled data, and then run the algorithm on the particular cube you want to interpret. So, as I said, you can use your seismic attributes as feature, but then the main question is how many seismic attributes, which ones, what's the meaning, what's the physical and geophysical meaning of those attributes. Again, here you need to understand the geology a bit, and you need to apply that to the feature selection. Of course, you can use PCA for dimensionality reduction, but you need to understand which seismic attributes are more meaningful in terms of geological understanding. And with that, I leave a page of references, of course, for anybody that is more interested. And that's it from my side. Thank you for listening.
Okay, thank you very much, Luca, for your well informative presentation. I see there's a question in the chat box that talks about so it says Bar Osman asked if the volcanic carbonate buildups and salts look alike on the seismic, how can we distinguish and identify each of them?
Yeah, that's a, a very good question. Of course, they look similar at the first glance. Normally, there are features that can discriminate the different objects. Okay, for example, salt is normally kind of transparent, so you don't see any stratification below the top of the salt, while in a carbonate buildup, you will see geometries that they are suggesting a growing of this feature through time. And volcanics, of course, will be very, the top and the base will be very clear, very sharp. For salt, you won't see the base. So there are different characteristics that can help in understanding what you're looking at. And also a part of it is your regional understanding of the area. Okay, if you know that in that area, that particular geological era, there were some volcano, and you see a feature like this, then you start to at least to test the hypothesis that that particular object is a volcano. So yeah, it's a combination again of geological understanding and also the experience with this kind of objects in seismic lines. If you have seen already reefs and carbonate buildups in other seismic lines, then you can compare and see the similarity or the differences.
Okay, thank you very much. So another question from Bara Osman again. It's about the supervised model, about labeling the training data. As you mentioned, when you're labeling the training data, you would say this is a fault or a horizon, if I'm not mistaken.
Yeah.
And is it a specific horizon or just that's characterized by a continuous signal?
Yeah, of course, it depends on the seismic data that you are looking at. It depends on the quality of the image, of course. But basically, you will pick some faults and pick some horizons, and those will be the training data for the particular algorithm you're using. Okay. And you can also, of course, then refine maybe the first result of the algorithm and do some sort of um, refining of the interpretation and telling the algorithm where he got it right and where he got it wrong. But yeah, basically what you do, you will be picking horizon and faults and use those as an input for the algorithm.
Okay, nice. So if there is no more question, I would like to thank you again, Luca, for your time and help and giving this presentation to us.
Yeah.
Thank you. So I would like to share and Osman, thanks you as well for your answer. I would like to share my screen to, I hope you can see it now. So we will have a very interesting session tomorrow. If you haven't registered for the session yet, so it's part of, oh, sorry. So it's part of a special geothermal talks that we hold on through Geo Hackathon. Sorry again. So if you want to register for the session, which will be held tomorrow at 16 CET, you can either scan this QR code. If you cannot do a scan right now, I also put the registration link on the Discord channel, on the general channel. So feel free to register there and receive the link of the presentation. Also, we will be hosting a Krill Sirayev on Friday, 13th of October. From GeoSuffer, he will be talking about the seismic inversion and reservoir characterization. So thank you again, all of you, and hope to see you in next sessions.